Okay, so just a quick reminder that the attendance code is 5915. 5915. So in chapter 5, this is a very important slide here that summarizes concepts about work, energy, kinetic energy, potential energy, and so forth. And just to quickly remind you, we classified forces into two types, conservative and non-conservative, so that in this work energy theorem here, where the net work done on an object as it moves between 2 points is the change in its kinetic energy, this left side can be broken up into work done by non-conservative forces like friction and work done by conservative forces like gravity. And today we're going to introduce another type of conservative force, and that's going to be the spring force. So we'll attach some mass to a spring and it's going to oscillate back and forth. And we will see that just like gravity, the spring force is also conservative, which means that you can calculate the work done by the spring force as this mass attached to a spring moves back and forth, simply by calculating the change in some spring potential energy analogous to the gravitational potential energy. So that's the concept we're going to introduce today. So here is the spring force. First, it is a conservative force. The work done, just like gravity, the work done by the spring force can be recovered. And so, for example, when this gymnast comes down onto this springboard, she's starting out here up at this height. If she jumps from rest from some height, she has some gravitational potential energy, mgh. As she falls, it gets converted into kinetic energy, right? It gets converted into some 1/2 mv squared. And then as she hits the springboard, the spring force will now exert an opposing force, and then she will start to slow down, and the spring will get compressed, and eventually she'll come to a stop. So now all of the kinetic energy is gone, but it is now stored in spring potential energy, because we know what's going to happen next is that the springboard is going to shoot back up and launch her back up into the air, right? So there's a conversion from gravitational potential energy to kinetic energy to spring potential energy, and that's the concept that we're going to introduce today. Any questions on that? Oh, actually, I had a quick top hat question before we get into this, just as a refresher for you. Let me do start presentation. Just as an application of the work of all these energy concepts, let's see as a quick recap question. See if you guys can do this problem. An object of mass 5 kilograms is dropped from a height of 1 meter above the ground. What is the speed of the object just before it hits the ground? So again, there's some object that you release from rest 1 meter above the ground, and then what is its speed when it hits the ground? So again, think about at the very top, it has no kinetic energy, it has only gravitational potential energy, mgh. That's being converted into kinetic energy. So use the conservation of energy to figure out what is the speed with which it will hit the ground. Any questions about the question? And of course, G here is 9.8 meters per second squared, right? So feel free to use that. The top hat attendance code is 5915. Twenty seconds. Let me add 15 seconds. Okay, let's see what we got. All right, it's kind of, let's see what the correct answer is. All right, so it's kind of all over the place. The correct answer is there were 13 that had 48.9. Is there some decimal issue? Why are people getting 49? Oh, I see. Right. So some of you just computed the MGH, I guess. Right. So let's just do that. Let me just unpack that real quick. So again, the idea here is that you were asked, so here's the ground. There's some object here. It's dropped from rest and it falls down. And so the initial energy here is just mgh. The only force acting on it as it falls down is gravity. It's a conservative force. And so therefore energy is conserved. And then when it hits the ground here, it has some final energy, which is just 1/2 mv squared. Because remember, so this is like our y equaling to 0. Remember that the energy is kinetic energy plus potential energy. So up top here, the object is released from rest. Why is this? Why does this pointer not work? Okay. So up top here, the object is released from rest. So it has 0 kinetic energy. It only has gravitational potential energy, mgy, and the y here is h. So up here, y is equal to h. And so therefore its total initial energy is that. Its final energy down here, the potential energy is 0 because it's mgy and y here is 0. So it only has kinetic energy, which is 1/2 mv squared. And so by conservation of energy, the final energy is the same as the initial energy. And therefore 1/2 mv squared is equal to mgh. And therefore the m cancels on both sides. And then v squared is 2gh. And so therefore v is the square root of 2gh. And that is the square root of 2 times 9.80 meters per second squared times 1 meter. And what does that come to? 4.427 meters per second. Any questions on that? Okay. So let's now come to the spring force. So again, the same thing as this problem that we just did. Yeah, go ahead. I'm assuming the arithmetic there is right. I didn't check. Yep. In some sense, this thing where this gymnast is jumping onto the springboard, the first part of the problem is very similar. MGH is getting converted to 1/2 mv squared. But now when she lands on the springboard, that 1/2 mv squared is now getting stored into spring potential energy. And so that's what we will now talk about. So here's the way springs work. So what you're looking at here is a spring that is relaxed. It is neither stretched nor compressed. So so here's a spring, right? And if I just let it be, it's happy, it's sitting there, then it has some natural length, and I will just choose a coordinate system that the end of the spring over here, I'll call that x equaling 0. That position I'll call x equaling 0. It is completely relaxed. It is neither compressed nor stretched. Now, if you were to give this spring a push to the left like this, and then you will end up compressing the spring, and let's say you compress it by some amount d, then that is a compressed spring. Or you could pull on the spring to the right, and in that case, you are stretching the spring. Now, you know that when you compress the spring, you will feel that the spring is going to be pushing back on you. And when you pull on the spring, you know that the spring is going to be pulling on you the other way. So the spring force is a restoring force in the sense that when you try to compress the spring this way, the spring wants to push back and get to the origin. And if you try to pull it in this way, then the spring wants to pull back and get to the origin. So the spring force is a restoring force in the sense that it wants to come back to this relaxed position, x equaling 0. And if you displace it from that position, it doesn't like it, and it will exert a force in a direction that is going to try to get you back to the origin. Any questions on that? So this is quantified by a spring force law called Hooke's law. And Hooke, by the way, did you guys see the Cosmos TV show with Neil deGrasse Tyson when it came out a couple of years ago or something? Anyway, he has a whole thing there about Hooke. Was an interesting character. He had lots of fights with Newton and stuff like that. So anyway, this is somebody in the Zoom said yes in all caps. Awesome. Really, nobody saw Cosmos? Okay. Yeah, whatever happened to that show? I guess it got canceled. I can see why. Nobody heard about it. All right. So Hooke's law says, this is sort of a quantitative expression of what we're describing here. It says that the spring force will be proportional to the amount x that you displace it from the origin, right? So if this is x equals 0, then if I stretch it by this amount d here, then this x is d. And if I compress it by this amount d here, then the x will be minus d, right? Just let's assume again that the positive x direction is to the right. That's our positive x. Then if I stretch it this way, then I've stretched it by an amount plus d. And if I push it this way, then the new x coordinate here is x equals minus d. And the spring Hooke's law basically says that the spring force will be proportional to the amount that you stretch it or compress it. The constant of proportionality is called the spring constant. And again, we feel this, right? The more you compress the spring, the harder it pushes back. And that's basically the statement here, that the bigger the x is, the more you displace it from its relaxed position, the greater the force is. This is the constant of proportionality called the spring constant. And then we stick in a minus sign here. It takes care of the fact that the spring force will always be opposite to the way you've displaced it. So let's actually go to the next page for that. So let's imagine that you've attached some mass to the spring here, and the spring is now relaxed. Everything's at x equaling 0. According to Hooke's law, when x is equal to 0 here, then the spring force is 0. But now let's say you compress it by some amount. The new position here is x equals minus d. So if I stick that into Hooke's law, I will get that the spring force is minus kx, but now x is minus d. And you see that the two minus signs cancel. And the spring force is k times d, which is now positive, which means what? It means that the force vector is pointing to the right in the positive x direction. So that's why that minus sign is in there. It just takes into account that the spring force is always opposing any displacement from equilibrium. Similarly, if I look at the stretched spring here, in this case, the x is plus d. So then I end up with minus k times d, and minus k times d is negative. And that's simply saying that the force here being negative means that it's pointing in the negative x direction. It's pulling towards the equilibrium position. Any questions on that? Okay. Okay. So next, what we're going to do is we can ask the question that, if you take this mass and you stretch it by you compress it by some amount d, or you stretch it by some amount d, you can ask, what is the work done by the spring force? This is completely analogous to if you take an object and you lift it by some height, or you lower it by some height in a gravitational field. You may ask, what is the work done by gravity? So in the same way, when you stretch this spring or compress it, you can ask, what is the work done by the spring force? And because it's a conservative force, I should be able to write it as minus the change in some spring potential energy. And that spring potential energy will be a function of this x coordinate. So in other words, if I stretch it from x equaling 0 and I move it all the way to x equaling d, then I should be able to evaluate the spring function, spring potential energy function at x equaling d, and I should be able to evaluate at x equaling 0, take the difference, and from that I should be able to get what is the work done by the spring force. And so what we're going to do here is we're going to discover what is this spring potential energy function. So again, just to kind of give you the analog in gravity, the work done by the gravitational force is minus the change in the gravitational potential energy. And remember that the gravitational potential energy was a function of y, which was mgy. Right? So in the same spirit, what we want to say is that the work done by the spring force is minus the change in some spring potential energy. And then the question is, this spring potential energy should be some function of x, the amount by which you stretch or compress the spring. What is that equal to? What is that function equal to? That is what we want to figure out. Because once we have that function figured out, then I can use energy conservation, kinetic energy plus gravitational potential energy plus spring potential energy must be conserved in a situation where there are no non-conservative forces, for example. Any questions on that? Now, what's a little bit more tricky in this case is that unlike the force of gravity near the surface of the Earth, what is the force of gravity? It's just mg, right? So it's a constant force near the surface of the Earth. But for the spring force, it's not a constant force, because you can see by Hooke's law, the magnitude of the spring force changes depending on how much you stretch or compress the spring. Whereas with a mass in a gravitational field, whether it's 1 meter above the ground or whether it's 2 meters above the ground, the gravitational force is just mg, it's just its weight. Whereas the spring force really does depend on how much the spring has been stretched or compressed. So therefore, this spring force is not constant. It's a force that varies with position. Again, in gravity, the force does not vary with position. As I move the object up or down 1 or 2 meters, the force is just mg. It does not depend on the y coordinate. Whereas here, if I move the spring back and forth, the value of the force changes depending on what the x position is of the spring. Now, the way we did this in gravity is we basically did this calculation, right? The work done by any force is Fd cosine theta. And so we looked at an object and moved it by some height. The F here was just mg, the d was just the height, and then the cosine theta was the angle between the displacement and the force. And we were able to immediately compute this work done and then discover that the gravitational potential energy was mgy. But you can see that there's a problem if I try to do this with the spring force, because what if I displace the spring by some amount d, I don't know what value to put for this spring force here, because as I'm stretching the spring, at every point the force is different until you arrive at this final position. Does that make sense? So when the object is stretched by this much, there's some spring force. Then when I move it to this new position, the spring force is even bigger. And then when I move it to this final position, the spring force is even bigger. And this is the total distance d that I've traveled. But I don't know what value of the force I need to put here, because at every point in that journey, the value of the force was changing. So the strategy that we're going to use is that we can compute this work done by simply using what is the average value of the force in that journey. So if I can figure out on average what is the force, so down here the force is when you stretch it by that much, this force is very small. Then it gets bigger, then it gets bigger, then it gets bigger, then it gets bigger, and then here it reaches its maximum value. It's a linear function of x. So I should be able to figure out what is the average value for the force here, and then just stick that in here, and then that will give me the work done by the spring force. If you've taken calculus, then you would do this using integral methods. But here what we're doing is equivalent. In the algebra way of doing it is that we first just figure out what is the average value of the force and then compute the work. So that's the statement here. We'll just compute the average value of the force and then multiply it by the displacement. And then that should give us the work done. And so if I were to plot this Hooke's law force, let's imagine that we take the spring and we stretch it from 0 and we pull it and we stretch it to the position x. Right, so we take it from here and we stretch it to some position x. What does the force look like? The force is minus kx. That is the equation of a straight line. Remember the equation of a straight line, y equals mx plus b. B is the intercept. Here the intercept is 0, so that's where you're starting here. M is the slope. So here the slope is minus the spring constant, so it's a negative slope. And then it's just a straight line. So if I were to plot it, the spring force would look something like this, right, as a function of x. Any questions on that? So as I'm pulling the object to the right, there's a negative force pointing to the left that increases in magnitude from 0 all the way to this minus kx. Any questions on that? And because this is a linear function of x, the average value of the spring force will be just in the middle, right, between the 0 and the x. So whatever this intersection here is, that is going to be the average force. And again, that middle value will just be the average of the initial and final values. Right, so if you step on the gas and you go from 0 speed to some final speed at a constant rate, then your average speed will just be 0 plus your final speed divided by 2. So same thing here, the average force will just be the average of this initial force and the final force. So Fs evaluated at x equaling 0 plus Fs evaluated at the final x coordinate, the average of them, that'll be 0 minus kx over 2, which is minus kx over 2. So the average value of the force is minus 1/2 kx in that journey going from stretching the spring from 0 to x. Any questions on that? All right, and so then I can go ahead now and compute the work done by the spring force. It's just the average value of the force multiplied by the amount that it has displaced. And so therefore it is this minus kx over 2, which is the average value, times x. And therefore that is equal to minus 1/2 kx squared, just this multiplication. And this is supposed to be minus the change in the spring potential energy. So we have found an expression for the change in the spring potential energy as you stretch the object from 0 to x. Any questions on that? Let me just do it this way. But what is this minus the change in the spring potential energy? That's minus the spring potential energy value at x minus the spring potential energy value at x equaling to 0, right? And again, just like in gravity, we can pick what our reference level is, and I'll just choose that when the spring is relaxed, I will declare that its spring potential energy is 0, and then I will just measure the spring potential energy relative to that, because it's only the change that matters. And so therefore I will go ahead here and set this to 0. And so then you will end up with the result that therefore minus 1/2 kx squared, which is what we found above, is going to equal minus the spring potential energy at the value of x. And then this leads us to this result that the spring potential energy function at the location x is 1/2 kx squared. So this is the main result. This is analogous to the gravitational potential energy as a function of y, which was mgy. You can see that the gravitational potential energy had a linear dependence on the position. The spring potential energy has a quadratic dependence on the position. Any questions on that? So here is, in some sense, a summary of the work energy theorem. So remember that in the work energy theorem, the work done by all the non-conservative forces is just equal to the change in the total mechanical energy of the system. And the change in the total mechanical energy of the system is the change in its kinetic energy plus the change in its potential energy. The gravitational force, which is conservative, has a potential energy function, which is mgy, and the spring force, which is also a conservative force, it has a spring potential energy function, which is 1/2 kx squared. So if you have a problem that involves gravity and springs all together, then this statement here becomes that the work done by all the non-conservative forces is equal to the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the spring potential energy. All of that together is the change in the total energy of the system. Or another way of saying this is that the total energy of the system at any given moment is the kinetic energy plus the gravitational potential energy plus the spring potential energy. So going back to that gymnast that was jumping onto the springboard, as we analyze her motion, we're going to take into account that she has kinetic energy, she has gravitational potential energy, and she has spring potential energy. And as she's going through the motion, the energy will be transferred back and forth between these three different components of kinetic energy, gravitational potential energy, and spring potential energy. Any questions on that? All right. So I think all of this is best illustrated by doing a particular problem. And so let me go ahead and do that next. View seamless. Okay. So here, let's analyze this particular problem here. We are told that a 50-kilogram circus acrobat drops from a height of 2 meters straight down onto a springboard with a force constant. This K here is 8 times 10 to the 3 newtons per meters. Notice that the spring constant has units of newtons divided by meters, because this is newtons, this is meters. So K will have units of newtons per meter. And by the way, what is the spring constant K here? The bigger the K is, the stiffer the spring is, right? In other words, as K is bigger, then when you compress it by some amount, you'll get a bigger force. And if K is very small, then the spring is much more looser or slack. It's not going to push back as hard when you compress it. So now the question is, by what maximum distance does she compress the spring when she lands on the spring? So in other words, she's going to land on the spring and the spring is going to compress by some amount. And the question is, by what amount does the spring compress? So here's what I'm going to do. I'm going to draw a picture of what the situation looks like initially before when she's at the very top initially. Actually, before that, let me just say that in this problem, energy is conserved. Right, because the only forces at play here are gravity and the spring force. So if I think of the energy of this entire system, energy is conserved here. So initially, let's imagine that, so here's the acrobat, which I'm going to draw as a square of some mass m. And then here, down below, is the spring, which is now relaxed. It is completely unstretched. So there's the spring like that. And then what happens in the final situation? In the final situation, she will land on the spring, and the spring will compress by some amount, and then she'll come to a stop before the spring then bounces back, right? So in that situation, the spring will have compressed by some amount, maybe by that much. So now it's much more compressed, right? And the spring has kind of stopped at that particular location. Any questions on that? And the statement is that in this situation, there was some initial energy, and in this situation, there is some final energy, and they have to be equal to each other. There has to be a conservation of the total mechanical energy. So therefore, the initial kinetic energy plus the initial gravitational potential energy plus the initial spring potential energy has to equal the final kinetic energy plus the final gravitational potential energy plus the final spring potential energy. Any questions on that? Now, initially, she's starting from rest up here. She's just kind of dropping from some height. So therefore, this initial kinetic energy is just 0, right? She starts at rest. Also, when she comes down here and she comes to a complete stop, the spring has compressed and then now she's come to a stop. So down here also, the final kinetic energy is also 0, right? So she hits the board with some speed, but then the board compresses and then brings her to a stop. So her final kinetic energy there is also 0. What about the initial spring potential energy here? Does anyone see what I would put for that? It would be 0, that's correct. Because here the spring is relaxed, It is in its equilibrium position. It is neither stretched nor compressed. So even the initial spring potential energy here is 0. Any questions on that? And so then you're just left with the initial gravitational potential energy is equal to the final gravitational potential energy plus the final spring potential energy. Now, I can simplify this even further. What I could do is I could just declare that in my I can choose a coordinate system where I'll say that this here is y equaling to 0. That is the final location where she comes to a stop. I will just say that that's y equaling 0, right? So then this here will be y equaling 0. And then it means that this height here, the amount that the spring has compressed, let's call that d. So it has compressed by some amount d. And we are told in the problem that she starts out with some height h above the board. So we were told in the problem that she starts 2 meters from a height of 2 meters straight onto a springboard. That means this h here was 2 meters. And by what maximum distance does she compress the spring? So this d is exactly what we want to find. That is the thing that we're trying to find. Any questions on that? So now, with that said, what can I say about the final gravitational potential energy? Well, that's going to be 0 because it's mgy, but here my y is equal to 0. I've chosen my reference level y equaling 0 to be over there. So this is kind of an amazing equation. It literally says that the initial gravitational potential energy that she had has been completely converted into the spring potential energy through the compression of the spring. Any questions on that? And so now what do I do for this? Well, the gravitational potential energy is mgy. But anyone see what I will put for y here? Not remember our y equaling 0 is here. So we have to measure the height of this thing relative to this. So it's actually 2 plus this extra d, right? Because that's where we set our y equaling to 0. So therefore, the initial height there relative to y equaling 0, let me say it this way here. Over here now, the y is equal to h plus d. So therefore, I'm going to come here and it's going to be h plus d is equal to the spring potential energy, which is just 1/2 kx squared, where x is how much it has compressed. That's going to be 1/2 k d squared. Any questions on that? And now we have an equation to solve for this variable d, which is how much the spring compresses. Now, unfortunately, this is a quadratic equation. It's not that unfortunate, right? It's just a quadratic equation. It's okay. Because there's a d squared here, there's a d here, and then there's a constant term here. So it's okay. You stay calm. You be zen about it. There's a quadratic formula. And you go one step at a time. So remember the quadratic formula. Is that ax squared plus bx plus c is equal to 0. Actually, maybe I should write this in blue, just because it's a segue. I'll do here ax squared plus bx plus c is equal to 0. And remember that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. You can use that at parties. Any questions on that? So what I'm going to do is I'm going to rewrite this formula in this form. I will have 1/2 kd squared. Then I will have minus mgd, and then I will have minus mgh is equal to 0. So the dictionary here is that the x variable here is like the d variable that we're solving for. And so if I just do a comparison here, I will get that your x here is synonymous with d. The a here will be 1/2 k. The b here will be minus mg. And then the c here will be minus mgh. And therefore, your d is now going to be minus b, right? This minus b here. B is minus mg. So that's going to be minus and minus will be plus. I can just write it out. Minus mg plus or minus the square root of minus mg squared, b squared, minus 4ac, 4 times k over 2 times c is minus m minus mgh, all divided by 2 times a, which is k over 2. Just using the quadratic formula. And if I simplify that a bit, that will just give me, therefore, d is equal to mg plus or minus the square root of mg squared plus 2k mgh, all divided by k. So we have two solutions to this quadratic equation. Notice that this negative solution here with a negative sign here is unphysical, because that'll give you a negative value for d. And d is, by definition, it's a positive number. It's the amount by which the spring is compressed, right? Because this number here in this under the square root is bigger than this, because this is just mg. This is like mg plus something else. So therefore it's bigger. So therefore this negative sign here will give you a negative answer. So the physical solution is just with the plus sign. And so let me just go ahead here and do copy. So the physical solution will have just a plus sign. Maybe I'll make that with a something like that, with a plus sign. And you can now go ahead and plug in numbers. All this information is given to you. So I can now plug in numbers. You know the mass of the Acrobat is 50 kilograms, G is 9.8. You know that K is 8 times 10 to the 3 newtons per meter. You know that H is 2 meters. So you know everything in this. You plug in numbers, and I think you get 0.560 meters. Somebody, let me double check that real quick. Yes, 0.560 meters. Any questions on that? All right, I think I'm out of time. So this actually brings us to the end of chapter 5. We will start chapter 6 after the break. And again, remember that your exam is, test 2 is this Friday in person. Mentally prepare for more people to be in class. I will see you guys on Friday.